Hey you guys, welcome back. So we're going to continue talking about the normal distribution. We've already defined what it is, and now it's time to start talking about how to calculate probabilities from a normal distribution. So that if I told you that SAT scores are normally distributed with a particular mean and standard deviation, you can answer questions like, what's the probability that a random person who took the ACT scored less than or greater than a particular value? So let's get started. So as a reminder, the normal distribution is actually a whole family of distributions. They all have this bell-shaped curve feature, and they all follow this particular formula right here. Where they differ is in their particulars, specifically what the average of that distribution is and how widely dispersed the values are. Or in other words, the mean and the standard deviation. But if you know that something is normal, and you know its mean and its standard deviation, you can figure out absolutely everything else that there is to know about that variable. You can calculate probabilities, for example. Now, I should say from the outset that you cannot calculate probabilities from a normal distribution by hand. You can't do it with paper and pencil. You can either use a table, like you probably have in the back of your textbook, or you can use Excel. My personal bias is I don't think students should worry about the tables in the back. Long gone are the days when statisticians had to use those tables. As a matter of fact, we can do almost all of our calculations without even converting to a standard normal, which is what those tables are about. So you can work directly with the distribution that you're interested in, and you can do that very easily in Excel or any more, of the more sophisticated statistical programs. So let's say that you've got a standard normal variable. So there I notice I say that probability of z being less than a particular number. That's kind of the convention where if we're dealing with a non-standard normal, probably use x's or y's or something like that. But the letter z is typically reserved for standard normal variables. So this here is a standard normal. We can see that it is centered over 0, like a standard normal is supposed to be. And it's got inflection points right here at 1 and -1. So we can tell right off the bat that this is a standard normal variable. Okay. Now, what is the probability that z is less than 1? Now, this one doesn't require Excel. We know that standard normals are symmetric and they're centered over 0, which tells us that half of the probability has to be to the left and half has to be on the right. Now the question asks, what's the probability that we're less than the midpoint? And so that's got to be 50%. So that one doesn't even require Excel at all. What if we're told that a variable is a standard normal and we want to know the probability that it is less than 1? Now one thing I'm going to do in all of these cases is start off with a drawing of a normal distribution. And when you're starting out, I really strongly urge you to draw the standard normal curve. You're going to be tempted to just think of it as a waste of time and you're too smart for that. But don't be too smart for that. Draw it. It'll take you 10 seconds. I think it's worth it. It really helps catch silly mistakes. And who wants to make silly mistakes on an exam or something like that? So we start out with our drawing of our standard normal. We know that the mean is 0. So if we're asked what's the probability that z is less than 1, I know that's something to the right of that peak. We're asking what's the probability that z is less than 1, so I shade everything to the right of 1, excuse me, to the left of 1, on this side of 1. Now I know that to the left of the center line is 50%. And so the number that I should get is something more than 50%. Now, if you hadn't drawn that, you might not have come to that conclusion quite so quickly. So drawing these graphs, I think, helps. Now we need to switch over to Excel and make the calculation. So let's do that. So we've got Excel open. I've keyed in here just a reminder what my question is. And let's see how we can use Excel to calculate this probability. Any formula in Excel starts off with an equal sign, so we put in equal, and then we type in norm, and then this is going to be a standard normal, so we put norm.s.dist, and then we open up our parentheses. And Excel prompts us for two inputs: the particular value of z, which in our case is 1, and then it wants to know whether we want a cumulative probability, which is essentially all of those, like imagine there were an infinite number of histograms for our normal, all of those little bitty histograms leading up to and accumulating to 1. So yeah, we do want that. And so we can put in a true there, or alternatively, you could just type a 1. In computer science, 1s are usually the trues and 0s are the falses. But you can type out true. Hit enter, and we get an answer. We get 84%. And that is reasonable for us. We knew that we wanted a number that was bigger than 50%, less than 100%, of course. And so that generally fits our intuition. I don't hear any alarm bells going off. 84% sounds fairly reasonable. Let's do another example. Now we might be asked, what's the probability that z is bigger than a particular number? Now here it gets a little bit tricky because Excel can't directly calculate any probability associated with a greater than sign. Excel's formulas only answer less than questions. So we kind of need to tweak Excel a little bit to give us the probabilities that we want. And the idea is to generally just use the rule of complements. So we can see here that here's 1, and Excel can give us this probability to the left. In fact, we just calculated it. It was, what, 84%, 83%? So if 83% is here, that's got to mean that 1 minus 83% has got to be here. So we're going to use this rule of complements, or this 1 minus probability, to answer the greater than question. So let's do that. Okay, so if we want to know what's the probability that z is bigger than 1, well then we got to use the rule of complements. It's going to be 1 minus the probability that it's less than 1. Oops, no, that's just a comment. I just wanted to point out what I'm doing. So now let's key in the actual formula. We start out with an equal sign, and we do 1 minus, and then the same formula that we had before. It was norm.s.dist, probability that z is less than 1, and it's a cumulative probability. In other words, we don't want just the height of that of the normal distribution. We want the area to the left. That's what true tells you. So we hit enter, and we get 15%. And 15% and 84% should add up to 100%. And I promise, it does. This plus this equals our 100%. It was pretty easy. Let's do another. You can use Excel to calculate areas, not just less than a particular number, but between two particular numbers. For example, what's the probability that our standard normal variable has a value between +1 and -1? Now, you might remember that there's an empirical rule concerning normal distributions, bell-shaped curves, which basically says that 68% of observations happen plus or minus 1 standard deviation from the mean. And that's what our z distribution really is all about. Its standard deviation is 1, so just moving over to a value of 1 is increasing by 1 standard deviation. If we were to increase to a value of 2 for z, that's an increase of 2 standard deviations. So how do we verify that 68% of observations lie between -1 and 1? Well, we can use Excel. And this is one of those places now when drawing the distribution I think is very convenient. Remember that Excel can only answer questions that deal with less thans. And here we've got probability that z is less than 1, and z has got to be bigger than -1. And so this bigger than thing is going to require some tweaking of Excel. Now, how do we get this area in the middle between +1 and -1? One approach is to calculate the probability that z is less than 1 and then subtract off the part that you don't need, namely the probability that z is less than -1. All right, so again, this probability is equal to z less than 1 minus the part you don't need, the probability that z is less than -1. And that's the kind of formula that you'll key into Excel. Let's do that right now. So I'll do this in just a couple of cells rather than doing it all in one particular cell. What we want is the probability that z is less than 1 minus the probability that z is less than -1. So how do we do that? The probability that z is less than 1, we already calculated up here. And the probability that z is less than -1, we calculated right here. So I really only need to just do this minus that. And so I could do that just subtracting these two cells. Or I could just do this all in one fell swoop. So norm s dist, the probability that z is less than 1 minus the probability that z is less than -1. And we get 68%, which is what our empirical rule said it should be. And this is, I think, why memorizing those simple kinds of rules is very, very useful. It helps you double check. So if you had accidentally keyed in a wrong formula in Excel, you'd be able to catch that mistake. So here's another question that's very similar to an empirical rule question. It's asking what's the probability that z is within 2 standard deviations from 0. Recall that standard deviation is equal to 1. So a value of 2 for z really is 1, 2 standard deviations to the right of the mean. And -2 is 2 standard deviations to the left of the mean. So this is a 2 standard deviation plus or minus range. We know that that probability should be approximately equal to 95%. That's one of our empirical rules. But we can verify that using Excel. Let's do that. Our procedure is going to be identical to the one we just had before. Excel can only calculate probabilities less than a particular number. But this question wants z less than 2 but bigger than -2. And Excel can't calculate the bigger than probabilities directly, but we can use a rule of complements or something like that. Or we could just remember that we want really this shaded part, which is the probability that we're less than 2, and then we want to take off, we don't want all of this, so we want to subtract off the part that's less than -2. So once again, we want probability that z is less than 2, but then we don't want to shade this part, so we subtract off the part we don't want shaded. So let's do that in Excel. Okay, so we want the probability that we're less than 2 minus the probability that the part that we don't want, the part that's less than 2. Key that in and we get 95%. So our empirical rules are right, at least according to Excel. This is a good thing, right? I love it when everything just starts clicking and all those pieces that we've been learning all semester, you start connecting them and everything starts making sense. So it's probably really obvious by now how to answer a question like this, but I wanted to do just one question where it wasn't symmetric. So it wasn't plus and minus 2 or plus and minus 1. Here we've got a slightly different kind of problem, but it's only slightly different. We want to know what's the probability that our standard normal variable is between 1.23 and 0.64. So I graph the normal curve. It's somewhere between 1 and 0.64. So I got two numbers and they're both to the same side of 0. I should get a fairly small number for that. Now Excel can only calculate less than probabilities, so we need to work within those constraints. Essentially, we want the probability that Z is less than 1.23, but I don't want to get all this part. This is the part I don't want. I only want this blue part. So I need to subtract off the part that's less than 0.64. Same kind of thing we did the previous two times. This is a cinch in Excel. Let's go do that right now. Okay, so I keyed in my question here. Now let's calculate it. We want the probability from a standard normal, right, that Z is less than 1.23 minus the part we don't want. The probability out of that standard normal that it's less than 0.64. Subtract those two and we get 15%. This also made sense given how we drew our graph. We knew it was going to be some number, it had to be less than 50%. We don't know much more about that, but at least we did get a number that was less than 50%. Now, why less than 50%? The entire probability to the right of 0, this entire probability here, has got to be 50%. And this is only a portion of that 50. So I knew I had to get a number less than 50%. And sure enough, we did. We've spent a lot of time just now talking about probabilities out of a standard normal. We don't have to restrict ourselves to a standard normal. We can answer questions from a non-standard normal, from any kind of normal distribution that you want. If you can tell Excel what the mean and the standard deviation is, it can answer any normal probability question for you. So here's a standard one. IQ is distributed normally, or at least it's believed to be. It's measured so that its mean is set at 100, and the standard deviation of IQ is approximately 16, maybe 15 or 16. We'll go with 16 right now. So you've been told that it's normal, you've been given the mean and the standard deviation. That's all you need to be able to answer any question about that distribution. For example, a question like, what percent of people have an IQ less than 105? So just reminding ourselves about notation, we're saying that IQ is distributed normally with a mean of 100 and a standard deviation of 16. What's the probability that IQ is less than 105? Notice I didn't use Z like before. We reserve Z's specifically for standard normal questions. This is not a standard normal. But we can use Excel just as easily to answer this question. So here I've got a reminder of what our data and our question is. And the question asks, what's the probability that IQ is less than 105? So all formulas start with an equal sign. We type in norm. This time we don't type S for standard normal because it's not a standard normal. We just do norm.dist. We open our parentheses, and Excel prompts us for more information than before. It wants to know X, and X was 105. And now it wants to know what is the particular mean and standard deviation, right? Mean and standard deviation there. Since it's not a standard normal anymore, we don't know. We have to tell Excel. And that mean was 100, and the standard deviation was 16. Then we just key in true, just like before, close parentheses, and hit enter, and we get our answer. So 62% of people score an IQ less than 105. Okay, one last example. Non-standard normal, and this time the question is asking, what's the probability that IQ is greater than 90? Recall, Excel can't directly answer questions about greater thans. It can only do less thans. So we just need to use the rule of complements. And the idea is the following. Got my pen. So we've got a normally distributed variable, IQ. Its mean is 100, and we want to know what's the probability of greater than 90. So I know I want to get a number bigger than 50% because just this part here, just this part is 50%, and I've got a little bit more. Now how do I do this greater than? Well, the area underneath the curve has got to be 100%. So if I take 100% and then I subtract off the shaded area, I'm left with this part right here, the part that I want. So again, the rule of complements, 1 minus the probability that IQ is less than 90. And that's all we need to do in Excel. Let's do it. All right, so I just typed myself a reminder about what my question is and the data for the question. And we just key in 1 minus norm dist. We don't do norm s because this isn't standard normal anymore. We give it the particular value of x that we're interested in, this 90. Then we got to tell it the mean for our particular question, which is 100. The standard deviation, which is 16. And then we always key in true there. Hit enter, and we get 73%. So it's really straightforward. Excel does all the heavy lifting for you. You just need to remember how to kind of tweak it to answer greater than questions. It's really straightforward. Hope you learned something. Thanks for listening.